Now we will generalize the concept of fitting a line in two-dimensional space to the given data set to fitting a hyperplane in higher dimensions. In regression, we call it regression with multivariables. The training data set consists of d-dimensional vectors and we have n observations. There are d features and in each data point or each vector, this is a sample which consists of an observation for the different features. The associated target values are real numbers and we have n real numbers corresponding to the n data points. The linear regressor can be, we can define it as an inner product of the data point with a weight vector plus W naught, where W naught is a bias or an intercept in case of a line, and the output is a real number yi. So for the each observation or the sample point or the data point, we have one corresponding output which is a real number, and for n observations we will have n such linear equations. The least square gives us the best fit which minimizes the error, and for getting the least squares done, the first step is to define two vectors, one corresponding to your observations and the other one corresponding to your the weights with which you take this linear combination. So this W vector is taken from this equation, linear equation. For each observation sample point or the data vector, we define a vector Sxi hat by adding 1 as the d plus first element, and the W hat vector is all your weights corresponding to the features, and then the intercept, or for the case of a line, and or a bias, and for the case of hyperplanes. In step 2, we can see that once we have defined the xi hats, we multiply the xi hat with the weight vector and we get the observation. In matrix vector notation, we can write this putting all the observation vectors in the form of a matrix, which is capital X hat, and multiply it with the weight vectors. This is same as putting all these linear equations in the form of matrix vector multiplication. And then we have the observation vector, which is represented by y, and its ith element is the real value y sub I. In this matrix vector multiplication, this is how the x hat is constructed, the matrix x hat. This is called the matrix of observation, or it is also known as the data matrix, and y is the vector of observations. Now for least squares, or the best minimum error in Euclidean sense, what we need to do is to minimize again the output of our linear model, its deviation from the observation, and then take the norm square. And the norm square is the length of the error. The norm square gives you the length of the error, as we discussed in the previous slides. Pseudo inverse is one option with which we can achieve this minimization. So let's see how the pseudo inverse is, how can we express the solution in terms of pseudo inverse. We want to minimize, the argument is to find out the weights. So we minimize over the weight vector this deviation between the vectors, the difference vector, or when we take into account the norm. So this is the square of the length of the error vector or the difference vector. Opening this norm square, so this is a minus b. This is similar to a minus b whole square, and I can write it as a minus b into a minus b. And when we are in matrix vector notation, then we write it as a minus b transpose into a minus b. So opening this product of these two vectors, we can write it as this can be expressed something like this. And for each vector or a matrix, the dimensions are given, and you can, as you can see, and further work on it to see that the rules for the matrix vector multiplication are not deviated. Taking the derivative from the calculus, we know that if we want to minimize an expression, we take the derivative with respect to the variable with which against which we want to minimize it, and then we equate it to 0. So taking the derivative with respect to the weight vector, this expression is reduced to the data matrix multiplied by the transpose of the data matrix into the weight vector minus 2 times the product of the data matrix and the observation vector. I can have from this equation I can have the expression for finding out the weight vector, and in this expression on the right side I have some matrices getting multiplied by each other into the observation vector. This term x transpose inverse into x, this is known as pseudo inverse. And if we have a square matrix, we can invert it if the determinant of the matrix is not 0, that is it's not a singular matrix. So when we have matrices with the number of rows and the number of columns being different from each other, then it no more is a square matrix. In that case, we can use pseudo inverse to find another matrix which can be used to multiply with the original matrix and get the identity matrix. So for fat and tall matrices, instead of having the normal inverse of the matrix, we have a pseudo inverse, and using this pseudo inverse in case of a regression, we can multiply it with the observation vector and get the weights which result in the optimal solution from Euclidean sense, that is that it minimizes the error. We can also say this, that it minimizes the sum of the length of the error vectors.